Hello, welcome to Unit 5 practice problems for past papers. So this unit's on power and stuff like that basically. So if you like this, subscribe type thing. So yeah, without further ado, let's do number 1. A system has a useful power output of 4.0 watts and a wasted power of 16 watts. What is the efficiency of a system? Okay, so the efficiency of the system is actually the useful power divided by the total power, right? So in this case, our useful power is 4.0 watts divided by our total power, which is going to be the useful and then the wasted, because that means that useful plus wasted is equal to total. So it's 4 plus 16 equals 20 watts. So then our 20 watts is our total power. And then this is the efficiency, so then this is equal to 20%, which is B. When an object of mass m is raised to a vertical height h, the gain of its gravitational potential energy is the change in EP. The change in EP and the change of h are related by the equation right here, where g is the acceleration of free fall. The definition of which physical quantity is needed to derive this equation. Okay, so in this case we want the definition of the physical quantity that is needed to derive this equation. So let's look at each answer choice. We see that acceleration is needed to be defined because it's part of this equation right here. The momentum is P equals mv, but we don't really need to know what v is to derive this equation. For power is work done over a certain amount of time. However, time is not related to this one. And then work done in this case is force times displacement, or S. And it turns out that this is the correct answer, mainly because if you look at this equation, you should know this equation, or the derivation of this equation. It's like this, right? And then you write these parentheses, and it turns out the change in h is displacement, and then mg is the force of gravity. So that means that EP is actually the change in work as well. An electric car travels at a constant speed of 70 kilometers per hour for 80 kilometers on a straight horizontal road and uses energy E from its battery. The total resistive force acting on the car is proportional to speed squared. Assume the electric motor is 100% efficient. How much energy is used from the battery when the car travels at a constant speed of 60 kilometers per hour for 80 kilometers on a straight horizontal road? Okay, so first things first, let's take the information from the second one. So these are just like small details that we need to consider. So for example, assume that the electric motor is 100% efficient. That means that no energy is lost, and it's all put into the car's speed basically. And then there's total resistive force acting on the car is proportional to speed squared. So that means that the F is equal to V squared is equal to some value K. Or where K is a constant. Okay, so since we know that, let's try and actually solve the problem. An electric car travels at a constant speed of 70 kilometers per hour for 80 kilometers on a straight horizontal road and uses energy E from its battery. And then question is asking is how much energy is used from the battery when the car travels at a constant speed of 60 kilometers per hour for 80 kilometers on a straight horizontal road. Okay. So, there's actually two situations here. In the first situation, we have a speed of 70 kilometers per hour, and we're traveling for a distance of 80 kilometers. And then additionally, for the second one, we have speed of 60 kilometers per hour for a distance of 80 kilometers. So the amount of energy that is actually needed is dependent on the force, the resistant force, basically, right? Let's just say that like energy is also like 1/2 mv squared, but this is like the kinetic energy. So yeah. If we look at this, we see that F over 4,900 is equal to K. Whereas, okay, so then this is equal to 4,900 K. If we do the same thing here, F over 360 is equal to K. F2, let's say. This is F1. So 360K is equal to force 2. And then we see that force 1 or force 2 is equal to 49 over 36. And we can see that the first in the first example, more kinetic energy is actually needed because there's a higher resistive force. And I'm pretty sure it's actually proportional. So then if, for example, initially for the first one, we have E, that means the second one is going to be 36 over 49E, which I'm pretty sure is A. A builder is holding a brick of mass 300 grams, drops the brick on his foot. What is a reasonable estimate of the change in gravitational potential energy of the brick? Okay, so you should know, it's a memorizable formula, that the potential energy is mg times the change in h. So the mass of the brick is about 3 kg. Make sure you have the right SI units. The gravitational is 9.81 millimeters per second square times, I would say, around like 1.5 meters. And this equals to something in joules. If you calculate this out, you should get about 30 joules, which is A. A crate of mass 50 kg is pushed a distance of 6.0 meters along a horizontal surface against a constant resistive force of 70 newtons. The crate moves at constant speed. It is then lifted at constant speed through a vertical distance of 1.2 meters back onto the back of a lorry. What is the total work done in this process? Okay, so first things first, you want to split this up into two situations because we see that it's moving horizontally as well as being lifted up. So let's just say like the first one is horizontal and the second one is going to be vertical. Let's draw a diagram. So the box here, so the kg, and then we have resistive force of 70 newtons. Let's say we're going to the right. And the crate is moving at a constant speed. So that means that the push force is also 70 newtons because it's a constant speed. That means that the forces here are equal. So the total work is the force times the distance. Our force is 70 newtons times 6.0 meters. Equals work. And we see that work here is 420 joules. Now let's do the vertical component. So we are being lifted with a distance of 1.2 meters and 50 kg, and we have two forces up and down, where this is F push force, or the pull force, I guess, but this is like F human, let's say. And then in this case, the bottom here is Fg. Fg's can be calculated by mass times gravity. And yeah, and this is about 490 newtons. So that means that it is being lifted up at also 490 newtons, because as it says here, we are lifting at a constant speed, which means that the resultant force is 0. So if you remember, we just did this, you're just using the same equation. Work is equal to force times distance, where our work is equal to 490 newtons multiplied by 1.2 meters. And this is about times 1.2, 588 joules. So in this case, our answer should be approximately D, because 420 plus 588 is around 1000. Let's try and read this first. So it turns out that here it's like 1.4 newtons, and then here 0.8 newtons. So force X produces a total power of 2.0 watts. When moving the block between time 3.0 seconds and time 6.0 seconds, calculate the distance moved by the block during this time interval. Okay. So power, in this case, you should know, is equal to the change in work, or the change in time, so then power in this case is 2.0 watts. So you get the change in work. Work in this case is force times distance over the change in time, which is 6 minus 3. And this is 2.0 watts is equal to the force, and what we saw here, the force here is 0.8 newtons, multiply the distance over 3, so 6.0 watts seconds is equal to 0.8 newtons. Oh my god, it actually looks so similar, but this is watts, W. And if you divide 0.8, you should get like 7.5, I think. 7.5 meters is equal to S. Number 7. Two blocks are on a horizontal beam that is pivoted at a center of gravity as shown in 2.1. The beam NB rotates when the string is cut, and the small block of a weight 2.4 newtons is projected through the air. As shown. Where is the string? Okay, so the string here, right, is cut, and then it gets thrown. It's projected through the air, so I'm guessing like, yes, okay. Shows the last part of the path of the block before it hits the ground at point W. So I'm guessing that it goes like this until it hits the ground, and then they give me a snapshot of this basically. Let's just say like this is the ground, but essentially it's just a snapshot of the entire path. At point X of the path, the block has a speed of 3.0 meters per second and is at a height of 1.8 meters above the ground. Air resistance is negligible. So calculate the decrease and gravitational potential energy of the block for its movement from X to Y. So we know that the change in EP is actually mass times gravity times the change in height. But we already know this because this gravitational constant is already given. So mass times gravity is actually 2.4 newtons. Is equal to change in EP times the change in height, which in this case is 1.8 meters. So then the change of EP is equal to 2.4 times 1.8 Newton meters, which is equal to 4.3 joules, rounded to 2 sig figs. Use your answer to C1 and the conservation of energy to determine the kinetic energy of the block at Y. Okay, so by conservation of energy, when we lose our potential energy, this actually turns into gaining kinetic energy. Right? So let's say that before, right? And this is actually equal to the after. So before, let's do kinetic energy first. So before, it's kg plus a change in P is equal to the change in EKE is plus the change in EP. I lied, it's not like change, but it's just the general sum of the potential and kinetic energy. So our kinetic energy before is 1/2. I don't think they give us a mass. So let's just do mass, I think. I think we can actually solve for mass because they give us the newtons, right? And we know our gravitational. So let's actually solve for the mass first. So mass, let's use doing this. So force is equal to MA, right? Our force is 2.4 newtons times mass kg times acceleration, which is 9.81 meters per second squared. So then 2.4 newtons divided by 9.81 is equal to mkg. So then m is about 0.245 kg. So we can actually replace this here. m and then v squared, our v is given for 3.4. Our potential energy is solved up here, so 4.3 is equal to our kinetic energy after, so our mass, and we actually don't know our velocity. That's what we're solving for. Plus 0. Okay, actually I kind of lied. So the question is actually asking for the kinetic energy, not the velocity. So we don't even need to set this equal. We just need to find this sum. This is because that although we have our EKE, we know that our potential is 0. So that's why we just only need to find the sum of these two. So you can just plug into a calculator. And it turns out this is 5.7 joules. Number 8. A car moves along a horizontal road with a constant velocity v against a resistive force F. The engine of the car has an efficiency of 0.25%, or not 0.25, 25%. What is the input power to the engine? Okay, so we know that power is equal to work over time, right? So you can actually convert this into force times distance, or it should be S, over time, right? So then this is equal to force times S over T, which is actually velocity. So our power in this case is F times V, which is actually given to us here. And we see that the engine of the car has an efficiency of 0.25%. So let's say our P output, or the power that we're actually outputting, is equal to F times V. We know that P output over the total amount of power is equal to 0.25, or 1/4, which is given here, the efficiency of 0.25. So it turns out that if we do P total is equal to P output over 1/4, we can substitute this P output, and we get P total is equal to 4 times M times V, which is C. Number 9, even though it says 16. A variable force is implied or applied to ensure that a constant power is supplied to a train. Which graph shows the variation of the force applied with the velocity of the train? So you should know that the velocity of the train is dependent on the resultant force. You should know from Newton's laws. I know I'm saying a lot of should knows, but a lot of these questions use a lot of different parts from previous units and just like build on each other. So I think I'll try to just get into it. But basically you just use Newton's laws, saying that F is equal to ma, right? If the resultant force of F is greater than 0 and our mass is constant, our acceleration is also going to be greater than 0. So that means that we're accelerating, right? Okay. So as force increases, our velocity is also increasing, and it's increasing with a concave up. This is because the change in v, right? It's accelerating too. So since it's accelerating, it's like a parabola going up. So yeah. But we have to be careful because f is actually on the y-axis, right? And then v is on the x-axis. So we know that, for example, if... Oh, that's a bad diagram. If we say like this, f is on the bottom and v is on top, as the force increases, our velocity is also increasing, right? But we have to flip our axes. You can do this by reflecting on the y equals x, and we see that if v is on the bottom and f is like this, we get a graph that looks something like this. So our answer is C. Thank you for tuning in to this part 1 of Unit 5. I hope you learned something, reinforced some background knowledge, etc. Yeah. Thank you for watching.